Okay, so we ended off yesterday with this question. We have the 1,500 kilogram car. Sorry, I forgot to write the mass in there. 1,500 kilograms. Okay, and it's being pushed down a 15-meter long ramp. Okay, and that force that is pushing it is 450 newtons. If that 450 newtons is going to act over 15 meters, what is it going to do? Four-letter word starts with W. Work. Exactly. Okay, there's going to be work done here. That means that the energy of the car will be greater at the bottom than it is at the top. Agreed? If I just put the car on the ramp, would it just go down the ramp on its own? It says it's frictionless, so it would just slide down the ramp. But then it would be a conservation of energy question. It would be like the roller coaster problems you did last year. The energy it has here and the energy it has there would be the same. But in this case, we're not just letting it go down the ramp, we're helping it down the ramp. Okay? Which means we're doing work and we're giving it more energy. Okay? So, if we can recognize that from the context of the question, then we know that we're dealing with a work energy theorem question. Okay? We know the energy is going to change. Okay? Now, what's the other way to calculate work besides change in energy? FD, force times distance. Okay, so can I say then that force times distance, and I know both of those numbers, I know the 15 meters, I know the 450 newtons, would equal the final energy minus the initial energy. Would that be true? It absolutely would. We just finished saying that the car is going to have more energy at the bottom than it has at the top. There's going to be a difference there between final and initial energies. Okay? All right, so let's expand this out a little more, because just like the roller coaster questions from last year, you start out small and then it just gets wider and wider and wider as you go along and include all the formulas. Okay? So I'm still going to keep force times distance over here, but I'm going to look at my final mechanical energy. Our final point is here at the bottom of the ramp. Okay, so normally I would say my final mechanical energy would be my final potential plus my final kinetic. That's how we calculate mechanical energy, right? Kinetic plus potential. Everyone okay with that from yesterday? Which one of those is zero? The final potential. Where are we at the end? The bottom of the ramp, on the ground, where our height would be zero. Okay, so at the bottom of a ramp, you can't slide any further. You have no potential to fall anymore. So this would actually be unnecessary, right? Because it's zero. All right, then I'm going to subtract from that the initial energy. I'm at the top of a 3-meter high ramp, so definitely have potential energy, and moving at 1.2 meters per second. So do I have kinetic energy as well? I do. I have both at the top. Okay? So this is the interpretation that goes into a work energy theorem problem, determining what kind of energy do we have at each point so that we can put it into this formula. Okay, they want me to find the speed at the bottom of the ramp. Which one of these three energy types would that be in? Which one of those energy types would have final speed in it? EKF. Okay, so next thing I'm going to do then is I'm going to isolate EKF. Before I put in all the formulas, it's easier to do it now. So if I want to get EKF by itself, what do I do with this whole bracket? I see people doing this. What operation do I do in order to do this? Add it. Yeah, do the opposite, right? I'm subtracting it. So let's see if this makes sense. Work plus the initial energy equals the final energy. Okay, does that ring true in your ears when I say that? Work, which is a change in energy, okay, plus the initial energy should equal the final energy. Yeah, that makes sense. Okay, so can I plug in formulas now? Can I expand this out again? So I'm still going to have force times distance, but now I'm going to add to that m times g times h initial, so my initial potential energy, and my initial kinetic energy. And that's going to equal my final kinetic energy. Okay. What am I trying to find again? Final speed, right. Sometimes it's easy to get lost in a question that's this long. You got to ask yourself, especially if you're old like me and forgetful. Okay, you got to ask yourself again, what am I solving for? Okay, so I need to isolate VF. What should I move right now then?
Divide by 1/2 m.
Right, divide by 1/2 m. Everything on this side is being multiplied. So if I want to move it, okay, so I moved that over there. Does the 1/2 of m cancel? It does not. Okay, in this case it does not because I'm adding on the top. I have to do the top and then divide by the bottom, so I can't cancel. If everything on the top was just being multiplied together, absolutely I could cancel, okay, but I can't here. All right, so this equals VF squared. What do I want? Just VF, so what do I have to do to both sides? Square root. All right, this kind of looks like the roller coaster questions then, doesn't it, from last year? Okay. All right, now I can plug in my numbers. I'm at the end here. Okay, so the force was 450 newtons times 15 meters plus 1500 times 9.81 times 3 meters. So there's my initial potential, plus 1/2 times 1500 times the initial speed, which was 1.2 squared, divided by 1/2 times 1500. Okay, so if I plug all of that into my calculator, okay, then I should be able to figure it out. I think it comes out to 8.3 if I remember from yesterday. Okay, 8.3 meters per second. Oh, come on. All right, so you got a couple of choices. This can get kind of crazy in the calculator. So what I do is I try not to enter it all at once, okay? Because I usually mess up a bracket somewhere and then my answer's wrong. Okay, so what I do is I go 450 times 15 meters. Okay, then I add that to 1500 times 9.81 times 3. And then I add again 0.5 times 1500 times 1.2 squared. Okay, and then I'm going to divide that by 1/2 times 1500, which is 750. Okay, and then I'm going to square root that. 8.3 meters per second. Okay, so now that I've got an answer, I should probably ask myself if that answer makes sense. Okay, car starts at the top of a ramp that's not that high, it's like 10 feet. Okay, and it's going to roll down that ramp with some help. Someone's also going to push it down the ramp. Is it logical to think that over 15 meters, it's going to go from 1.2 to 8.3 meters per second? I'd say that that's pretty fair. Okay, this is not an overly steep ramp. Okay, it's well, 15 long and 3 high, so it's not terribly steep. So it's not gonna pick up a ton of speed. That answer makes sense then. Okay, so when it comes right down to it, was there a lot of questions to ask yourself while you were setting it up? There was. Okay, was there a lot of algebra? There was. You have to move a lot of things around. Okay, but in the end, the principle is always the same. Work is a change in energy, in mechanical energy. Okay. All right. Let's try this one. Okay, similar idea. Okay, similar to the last question. This time, a crate is moving along a conveyor. And conveyors, like what they have at the, if you've been down to the bottle depot here, right? They got that belt and it takes all the bottles and it takes them up. Okay? So the conveyor uses gravity by being angled 15 degrees below the horizontal to allow the crates to roll down on the rollers, on the conveyor. Okay? Crates are moving at 0.75 meters per second at the top of the conveyor and accelerate to the bottom, which is 2.5 meters below the top. That's vertically. Okay? That's how high it is, not how long it is. Okay? There is a frictional force of 150 newtons along the length of the conveyor. Okay? At what speed do the crates leave the conveyor? This one's a little bit harder than the last one because there's one step in this one that wasn't in the last one. Okay? You have the height of the ramp and you have the angle of the ramp. You will need that to calculate something in order to get the work. Okay? Give you a little bit of time. Diagram that out and I think you'll see what you have to do that way. Okay, so that's the situation we're dealing with. Similar to last time, we're looking for the speed at the bottom of the ramp. But this time, it's not being pushed down, it's being resisted up. Okay, so does that mean it will have more or less energy at the bottom than it has at the top? Does friction usually impart energy or take it away? Takes it away. Okay, you're working against friction. Okay, those rollers are going to squeak and they're going to get hot and it's going to take energy from the box. So the box will actually have less energy at the bottom. Okay, just like anything that goes down a ramp that isn't frictionless, it's going to have less energy at the bottom because it's going to lose some to friction along the way. What's the thing you need to calculate before you can start this, really? Friction's going to do work, right? And we know the force of friction. What do we not know about that force of friction? Distance. The distance. We don't know how long the ramp is. That's the distance over which friction is going to work. Okay? If we don't know that number, we can't calculate the work done by the force of friction. So the first thing you have to do is calculate the length of the ramp. Okay? I'll give you a few more minutes before we do the rest of it. So I'm going to solve this two different ways. A few people asked some questions. I looked at how a few people did this. And a few people had the idea to do it what I would call the long way. It's absolutely valid to do it the long way, but know that it's the long way. Okay? It's not wrong, it's just a lot more work and it's a lot more steps. And on a unit exam where time can sometimes be a factor, I would suggest doing it the shorter way. Okay? But both work, and I'll explain why they both work. So first let's do it what I would think is the shorter way, or at least to me, the more logical way to do it, and that is to use the change in energy. The force of friction is going to take energy away because it's going to do work, okay? But this work is negative from the box's point of view. It represents energy lost by the box to the surroundings, okay? So I know work is being done, so I'm gonna set this up. Work is a change in energy, okay? And I'm gonna set up that means the force of friction, the thing doing the work, times the distance, which I don't have yet, okay, equals the final energy minus the the initial energy. All right, before I go any further, I know I need the length of the ramp. So I have the opposite side and I have the angle. Okay, so to get the length of the ramp, that's the hypotenuse. I'm just going to go 2.5 divided by the sine of 15. Okay, that will give me the length of the ramp. Okay, so 9.66 meters. All right, so that's the distance over which friction is going to act and take energy away from the box. All right, so now I'm going to say force of friction times distance, I have both of those numbers, is going to equal the final energy at the bottom of the ramp. What kind of energy does the box have? Kinetic only. It's at the bottom. There's no potential at the bottom. All right, so we're going to have EK final, okay, and then minus our initial. Do we have both kinds at the top? We do. We're above the ground, 2.5 meters, and we're moving at 0.75 meters per second. So we have kinetic and potential energy. So we'll have EP initial plus EK initial. All right, what I'm looking for, from here, it's basically the same as the last question. What I'm looking for is part of this. So what do I have to do with that? Add it to the other side. All right, so force of friction times distance plus EP initial plus EK initial equals EK final. All right, now I plug in my numbers. Force of friction times distance plus M times G times H initial plus 1/2 MV initial squared equals 1/2 MV final squared. And then I just do algebra. Just divide this over to that side, just like I did on the last one, and square root it to get VF, just like a roller coaster question from last year. Okay, it's just algebra. Plug in my numbers and solve. All right, so that's going to mean 150 newtons, that was the force of friction, times the length of the ramp, 9.66, plus 200 kilograms times 9.81 times 2.5, that was the potential energy, plus 1/2 times 200 times 0.75 squared, divided by 1/2 times 200. Okay, so if I punch all that into my calculator, so 150 times that number there, okay, plus 200 times, whoops, okay, sorry, I made a mistake here, guys. What mistake did I make with this number? I just put in answer, but I forgot to put something in with it, that it's negative. Okay, that's how easy it is to forget. Right? I just clicked answer and went right on. Okay, just thinking in my mind I had already done it. Okay, why do I have to make that work negative? It's friction. Friction makes you lose energy. Okay, so this work has to be a negative number. All right, so I'm going to have negative and then that number. Okay, then plus 200 times 9.81 times 2.5 plus 0.5 times 200 times 0.75 squared. Okay, and then divide that by 100 because that's half of 200, and then square root. Okay, so at the bottom of the ramp, they'll be moving at 5.9 meters per second. Okay, is that a number that makes reasonable sense? Seems to, okay? But I have to remember that they lost energy due to friction, okay? So that's the first way to do it. Believe it or not, I know I said that's the short way, believe it or not, that's the short way, okay? Because you really only do one thing, and that is work energy theorem. That's it, you don't do anything else, okay? Now, the other way to do this is to treat it like it's a Newton's second law question. All right, that means it's an inclined plane and there's all these forces that we have to calculate. All right, so if I look at it from a Newton's second law point of view, I'm still going to need to do this operation here where I calculate the length of the ramp. Okay, I'm still going to need to, and then I'm going to need to calculate forces. So I'm going to have to calculate the force of gravity. Okay, so 200 times 9.81, 1,962 newtons. Then I'm going to have to calculate F parallel, because I'm going to need that as well. So I got to calculate that, okay, because F parallel is here. Okay, so I'm going to have to go sine of 15 times 1,962. Okay, so that's going to be 507 newtons. Okay, can I calculate the net force now? What do you think? Is it okay to calculate net force at this point? Those are the only two forces acting, right? So I calculate the net force. Okay, so that's going to be that number minus 150. Okay, there's my net force. Okay, now that I know the net force, can I calculate the acceleration?
I got it.
Yes, I can, and I have to. Okay, so you see how many calculations I'm doing here? Is this a lot more steps already? It is. And every step is a chance to make a mistake. That's a really negative way to look at it, but it's also true. All right, so A equals F net divided by M. All right, so I'm going to get my acceleration here. So 357 divided by the mass, 200. Now I've got the acceleration, 1.79. Okay, I know the acceleration, I know VI, and I know D, so now I can calculate VF using an acceleration formula that I'll have to manipulate. I'm going to get the same number, right? I'm just going to go D equals VF squared. Oops, sorry, I already know D. Okay, I'm going to go VF squared equals VI squared plus 2AD. I actually don't have to manipulate it. Just have to plug the numbers in. 0.75 squared plus 2 times 1.79 times 9.66. Hopefully this comes up to the same number, otherwise I'm going to have done all this work for nothing. Squared plus 2 times that number times that number. Okay, and then I have to square root it. Oh, look at that. Came out to exactly the same number. But it was a lot of steps. I don't ever want to do a question with that many steps ever again. Okay, so I would prefer to do it with just work as a change in energy. It'll come out the same. Okay, and I've had people on the unit exam do a question like this way, and then at the end of the exam they're rushing to finish, and then when I show them the solution, they're like, oh, that question took me 15 minutes. Instead of, it might have taken them 6 or 7 to do it the other way. They just never thought, oh, I can solve this as an energy problem. Okay, now, here's what I'm probably going to do. If I put a question like this on a unit exam about work energy theory, I'm probably going to set it up so I don't give you enough information to do it the long way. Okay? That way nobody maybe thinks to do it the long way. Okay? Just because I don't want anyone to get challenged for time. Plus, a question like that, I want to assess your ability to do work energy theorem, not incredibly complex, long-winded Newton's second law problems. Okay? There'll already be a Newton's second law problem on there. Okay? I don't need to put 2. Okay, so here's the thing, guys. We need to understand that work changes the mechanical energy. That work can be positive, meaning it's going to increase it, or that work can be negative, meaning it's going to decrease it. The first example we did was a positive work example. This is a negative work example. All right? Everybody with me there? Okay. Now, I'm going to show you a quick video because our next question has to do with the scene from Raiders of the Lost Ark. The big round stone is 400 kilograms. I mean, it is after all a big rock. okay? It nearly runs him over. From a physics perspective, what height would the rock have to drop from? Drop, okay? If it rolls 30 meters against a frictional force of 800 newtons and was moving at 4.5 meters per second, it's about how fast he was running, okay? When it seals shut the temple. Okay, so we are looking for what height it was dropped from in order to make it moving at 4.5 meters per second at the end while working against 400 newtons worth of friction. Working against 400 newtons worth of friction. Okay, so we're going to have the rock here, okay, where it's dropped from. I mean, it didn't ever really fall in the video. It just kind of came down this track. Okay, so was it initially at rest?
Yes.
Yes. Okay, so we know that VI is 0, okay, and we don't know the initial height. That's what we're trying to find. What we do know is that when it's at the bottom, it has no height, right? So HF would be 0 meters, but we know that VF is 4.5 meters per second. Okay, we know it rolls 30 meters against this 800 Newton force. Okay, is that 800 Newton force taking energy away or giving it? It's taking it away. Okay, it's slowing the rock down. It's taking energy away. The rock made a whole bunch of noise as it rolled through that tunnel. Sound is a byproduct of friction. Okay, so we know that work is going on and that it's causing a change in the energy of the rock. Right? We know that the work is being done by friction, so we're going to go force of friction times distance. It's the only force that's causing the energy to change. Okay? Gravity doesn't cause energy to change. It causes it to convert from potential to kinetic. That's why we never put it in there. It actually doesn't cause a change, it just converts it. Okay? All right, so that's going to be then that's going to equal the final energy minus the initial energy. Here's where this question is actually easier than the other two. What kind of energy does it have at the end?
Kinetic.
Kinetic only. So I can say force of friction times distance equals EK final. What kind of energy does it have at the beginning?
Potential.
Just potential. Okay, so there's actually less algebra to do in this question here. All right, so what I'm going to do is I'm going to try and isolate initial height. It's part of this term. So I'm going to move it over here and then subtract the work. Okay, so what I'm going to have is initial potential equals kinetic final minus the work. Okay, now I'm going to plug in my formulas. M times G times H initial equals 1/2 mv final squared minus the force of friction times distance. I'm trying to find HI, so what do I do with the mg? Divide it over to the other side. Okay, then I just plug in my numbers. So 1/2 times 400 kilograms times 4.5 squared minus 800 times the distance, which was 30. But what do I have to do with this 800?
Make it negative.
I gotta make it negative. Otherwise, I'm subtracting a positive number. Force of friction and the work done by it are negative. Okay? And then I'm gonna divide that by 400 times 9.81. Okay, so 0.5 times 400 times 4.5 squared, okay, minus negative 800 times 30 meters, okay, divided by 400 times 9.81. All right, so that means it was dropped from a height of 7.1 meters. And that's about right. If you picture when he first heard the sound, he went like this. And he looked like almost straight up behind him. Harrison Ford's about 2 meters tall, okay? If he's looking like this, it's quite a bit taller than he is. All right? Does that make some sense? All right. Expect something around that for your unit exam. Okay? I'm not gonna give you one that's like outrageously crazy and has tons and tons of algebra. I wanna know if you can do this or not, okay? So something like that would tell me that pretty easily without having to do another 5 minutes of algebra. Okay.
Is this in the quiz tomorrow?
No, tomorrow's quiz is just friction and Newton. Okay, for tomorrow. Okay. All right. Where was the one I wanted you to try here? Okay, I want you to try this one. See if you remember that little change to the formula for work. This is nothing like what we just did. Okay, it's like way back. Right? Yeah. The formula for work last year was this. What did we add to it this year? Cos of theta, right? We put it right in the middle. F, cos of theta times d. We hadn't talked about it for a little while. That's why I wanted to throw one at you that had that in it. Okay? This is not being pulled in the same direction the work is being done. It's being pulled like this. Okay? But the box is actually moving this way, which means I only need the horizontal component of that force to calculate the work that it does. Okay, so if I know that this is 75 and I know that this is 20 degrees, what I'm actually doing here is 75 times the cos of, what do we got there, 20 degrees, okay, times, how many meters does it go? 10 meters. Okay, which is why we should get 705 joules. Okay, everybody all right with that? Okay. One like that would be a multiple choice question, by the way. Okay, because you don't have to do very much there. It seems like there should be a lot more to it, doesn't it? Especially after all those other ones we did. Okay, it seems like that's a little too easy. Okay, let's just look at this one. So a 20 kilogram box is pulled horizontally 9 meters along a level frictionless surface at a constant velocity. How much work is done on the box? None. Okay, why? You didn't accelerate it, so there's no change in kinetic energy. There's no friction.
Net force is 0.
Net force is 0, and it's also level. There's no change in kinetic, there's no change in potential, there's no change in energy. Okay? If work's a change in energy, we didn't do any work. Okay? It also wouldn't require any work to make something go at a constant velocity on a frictionless surface. It would do that on its own. Okay? You give it like a little kick, once it's moving, it's going to move anyway. Okay? It doesn't need my help. Okay? It'll just keep going. All right, does that sort of make sense? Could that be a multiple choice kind of question on a unit exam? Absolutely. Doesn't require any math, just requires you to understand. Okay? Okay, this one shouldn't take very long. I'm giving you that hint. Okay, it is a frictionless incline, and you're just pushing it up the incline at a constant velocity. Okay, I want you to calculate how much work would be required there. Okay, you can see that there is work required there. Okay, I want you to see if you can arrive at that answer, and then we'll explain why. Okay. So when it's at the bottom of the incline, it's moving at some velocity that we don't know. We don't need to know it because it's still moving at that velocity at the top, which means we don't change its kinetic energy. But does it still take work to push something up a hill? Because you're changing its potential energy. How much potential energy does it have at the bottom of the hill? 0. So all I have to do is go, all right, work is a change in potential energy. And that would be final minus 0, because it doesn't have any at the beginning. So all I have to do is say the work equals the final potential energy. M times G times H final. Okay, so that's 80 times 9.81 times 7, which comes out to 5,500 joules. Okay, is that also one that could be a multiple choice question? Yeah, because it doesn't require very much math, right? There's not a lot of steps there. Okay. Okay, everyone all right with that? So there's different ways. Yeah, in the written response, I'm probably going to give you one that's got a little more to do. Okay, but I could easily give you ones like this in multiple choice that still ask, do you understand what changes in energy are? Can you identify when one type changes and the other doesn't? Because those are important things that I want you to be able to do. Okay, does that make sense to everybody? Okay. Okay, I want you to try that one. It's also not a ton of work. It's not like the ones we did before. Okay, what does that need to be in? Meters per second, because a joule is a kilogram meter squared per second squared, not a kilogram kilometer squared per hour squared. Okay, so you got to make sure you have the right units. Is there another way for me to have done that? Could I have done a whole bunch of Newton stuff on that? And then done like force times distance at the end? I could have.
But I did.
Yeah, but it took a lot longer, didn't it?
Yeah, it did.
Yeah, okay. And that's not me trying to make fun of you. That's me trying to illustrate that point of, hey guys, yes, you can do this more than one way, but for God's sake, do it this way, because it's so much less work. Okay? The work energy theorem is going to be less work, and it's going to arrive at the same answer. All right, back to this one. Okay, I'm going to say this to you now. If you're still working on this, you're definitely doing it the long way. Okay, you'll probably get the right answer, but you're definitely doing it the long way. Okay, what kind of energy is changing about this car? Okay, so would the work done by friction be equal to the change in kinetic energy? How much kinetic energy does it have at the end? None. So would the work then simply be equal to the kinetic energy it has when it slams on the brakes? What's 55 divided by 3.6?
15.27.
Pretty sure that comes out to this. Boy, that was fast. Okay, now, if you were calculating acceleration and then net force and then saying friction was the only force acting and then going friction times distance, that's the long way. Okay, it'll work and you'll get the same number, but man, is it a lot more work than 1/2 mv squared and I'm done. Okay, so again, just trying to illustrate to you, if you can recognize that work is being done, the question outright says work, use change in energy if you can. You can always use force times distance, like that option's always going to be there. But sometimes finding those forces is a lot more work than just finding the change in energy. Okay, everyone kind of follow me there? Okay, like yeah, you could go through all of the effort of calculating all the forces and the acceleration and all of that, but why? Okay, this is much, much shorter. All right, I think we got time for one more here. Oh, or we don't, because Coder ran out of questions. Okay, I ran out of questions. There we go. Tomorrow is your quiz. Tomorrow's quiz is on friction and Newton. Okay, it's 6 questions. So go over questions from your, sorry, if you go over the practice quizzes I believe it's 5, 6, and 7. That's the kind of stuff that will be on there. In your digital workbook, there's a few friction-related questions. You could try those. Okay, there's a couple that have coefficient of friction in them. Okay, and one question that Mr. Dickey came up with that I was pretty happy with, so I stole it. Okay.